epsilon prime I alpha j alpha j minus epsilon prime beta j j I beta. And I'm going to write the first term a little bit differently. Write it again in terms of Kronecker delta. So I'm going to write epsilon prime. Instead of I alpha, I'm going to write this as beta alpha. But then I introduce a delta Kronecker function. So write that. So these together is epsilon prime I alpha. Okay, and you see why we write that in just a little bit. Again, you do the same thing to the second epsilon prime. Instead of beta j, I'm going to write this as beta alpha. And so I'm going to introduce a delta alpha j, j I beta. Okay. I'm going to do this. In the third and fourth terms. Okay, I'm going to introduce a 1/2 factor first. I'm going to write 1/2 of this plus another 1/2 of this, and then we'll play around with changing the indices and so on. Okay, 1/2 of epsilon prime beta alpha delta I beta j alpha j minus epsilon prime. Let me write it like this first to be perfectly transparent. Write it in the same way first, plus another 1/2 of exactly the same thing. Okay, epsilon prime. Epsilon prime. Third and fourth terms. Okay. So beta alpha delta I beta. Is that a real dog out there? Minus epsilon prime beta alpha delta alpha j j I beta. So nothing mysterious in here, right? So we split it off into 1/2 of that plus 1/2 of the same thing. Now, I proceed to do something. You see, in both this term and this term, wait a sec. I'm going to do something in here. Let's say we look at this first. Both alpha and beta are summed over. So therefore, I can change them, interchange them, okay? In other words, call alpha beta and beta alpha. We won't change anything, all right? So, not this one. Not this one. This one is exactly the same as before. I'm going to do it to this one and this one, where we change alpha and beta, because both terms involve a sum over alpha and a sum over beta, sum over alpha and a sum over beta. And so therefore, I can interchange alpha and beta. Interchanging alpha and beta, so here's beta alpha, so I interchange alpha beta of alpha beta. This beta becomes an alpha, this alpha becomes a beta. No different, since both alpha and beta are summed over. Do the same thing for this one in here. And interchanging alpha and beta, I have alpha beta. Alpha becomes a beta. Beta becomes an alpha. No different. Why do I do that? Wait a sec. I want to do that because because I want to take this factor out. Okay? Since this guy is anti-symmetric, so epsilon prime alpha beta is minus of epsilon prime beta alpha. So I can take all the epsilon prime beta alphas out. So let me do this very carefully, right? Now you just recall that. Remember that this is equal to minus epsilon prime beta alpha. And this one is minus epsilon prime beta alpha. So this minus together with this minus gives you plus. This minus together with this plus gives you a minus. And so altogether, taking out the epsilon beta alpha. Now, of course, you remember that the alphas and betas are still summed over in here. So I have 1/2. Let me write down explicitly the sum over alpha beta because I have changed the positions of the indices and so on and so forth so that there's absolutely no confusion. I'm writing back down the two summations that are meant to be done. And so epsilon prime beta alpha. And so I have delta I beta j alpha j minus delta alpha j j I beta. Here minus and plus becomes a minus delta I alpha j beta j. Okay, that's for this term. And then finally, minus and minus is a plus. Whoops, excuse me. Plus. Take out this factor, you have delta beta j, ji alpha. I am now in business. Because on the one hand, left-hand side in here, you have a linear superposition of all the epsilon primes, which are all linearly independent. Okay. Similarly, you have the same sum on the right-hand side. Okay. On both sides, alpha and beta are summed over, and therefore I can identify the individual coefficients, which means that this guy is to be identified with this guy. See that? And believe it or not, if you replace some of the alpha by I and so on, this is exactly the same equation as that one. I'm going to let you go home and verify that in detail. You can almost see it at this point, but maybe you want to sit down and kind of convince yourself, totally, absolutely, positively, 100% that the two equations are the same. Okay? So we are done proving the very powerful statement, the commutation relations for all the so-called generalized angular momentum operators. Those are the higher dimensional angular momentum operators. The only thing we haven't quite done is that we still have to prove that statement, which we kind of left out for the time being. So let's just try to go back to that and patch up that hole, so to speak. Okay. So we're going to prove that Fij as defined is an antisymmetric quantity, as defined like this in here. So let's take out this space. All right. So let's say we start off. Oh, by the way. There's a mistake in the notes. If you have the notes with you, if you don't, notice the equation 4.52. That I have given you. On the left-hand side of that equation, in the notes, it was written as Fij. It should actually be Fji. It should actually be Fji. Okay? Instead of Fij, I mean to write Fji. You see, here's the thing. You need to be very careful about these things, okay? A simple mistake like that could kind of make you screwed up royally, so to speak. Okay, so that's the thing with playing around with these tensor indices. You just have to be very careful with them. Okay. Now Fij was defined like this. So in order to write Fji, I just have to replace I by j and j by I in this definition, right? So let's write that down. And according to that definition, that must then be equal to B instead of I alpha. I have J alpha. And then BT, instead of beta J, I must have beta I. And then J alpha beta minus inverse of UB. Instead of Jij, I have JJI. UB. And now we look at the first sum. It is also a double sum over alpha and beta. And so therefore, as we have done before, we can flip alpha with beta, interchange alpha and beta. So in this sum in here, I'm going to do alpha interchange with beta. And so Bj beta, Bt alpha I, J beta alpha. Is that okay? The second term remains the same, minus first beta j, j I, UB. And now what do I do? BJI and oh, sorry, this is B. Okay, here's what I'm going to do. B T I alpha, I'm going to write as B I alpha, okay? B I alpha. So let me write this first. It's B I alpha. That's equal to BT alpha I by definition of the transpose. Okay? And then this one, I'm going to write as BT beta J. Is that okay? All right? By definition of the transpose. Now remember that these guys are anti-symmetric. So J beta alpha is equal to minus J beta alpha beta. So let's take a minus sign in here and write this as J alpha beta, like that. Okay? And so this, the second term is written in exactly, wait a second. The second term, this is JJI. Oh, the second term is written exactly the same way, except now I write JJI as minus JIJ. And so this becomes a plus. Whoops, sorry. Okay? I asked you to compare with this. I'm going to write, bracket this off, and change this plus to a minus sign, like so. The quantity within parentheses is exactly equal to Fij, as defined, okay? So I have proved that this is equal to minus Fij, as defined like this in here. So at this point, I have proved that Fij is equal to F minus Fji. So the F as a matrix is also anti-symmetric. Okay, so this is a final missing step. And we are done. And so we have proved this remarkable theorem, which is tremendously useful, I must tell you, which is tremendously useful. You can find many applications in physics, the first one of which is the commutation of the relations of the angular momentum operators in ordinary quantum mechanics. But then in cases where higher dimensional orthogonal groups are used in physics, you can use that for any n. As we said, you can find plenty of applications for SO4 in physics, one of which is the application to the hydrogen atom problem, finding all the energy eigenvalues of the hydrogen atom problem can be obtained by using the SO4 relation for this one. And then SO5 has applications also in condensed matter physics, in high energy physics, and so on and so forth. Probably you can come up with some applications for SO10. Those are mentioned as sort of like the one of the candidates of grand unified theory, unification of forces, and so on and so forth. But the verdict is not cast on that one yet. Okay? So since this is applicable to any n, so it's a very useful relationship indeed. And it's a little bit surprising and amazing that you can derive this general result for any arbitrary n. Okay? Nowhere did we use any information on the value for this number in here, because we're dealing at the same time with SON, where n is any possible positive integer. Okay? So with this, we end chapter 5. At this point, we want to go back to some general aspects of group theory in order to develop the subject a little bit further than we have. So far, we have focused on studying the Lie algebra corresponding to a particular Lie group. Now let's get back to sort of basic group theory. Yeah?
In the beginning, you started with the element B inverse AB.
I'm sorry, which equation?
In the beginning, we started with the element B inverse AB.
B inverse
AB. I'm wondering how did you know?
B inverse alpha beta? Something like that?
So B inverse times A times B.
The similarity transformation to start the.
Oh yeah, in the beginning we dealt with this element.
So how do you know to start with that?
Huh? How do I know how to start with that? I didn't start with that. Somebody else who proved that theorem started with that. It's well, the idea is you want to compare. You have to make use of group homomorphism property, or the group representation property. So you want to multiply different elements together, okay? And I guess the idea is if these are all infinitesimal rotation elements in whatever dimension, then you can compute things to first order in small parameters. And you need to have some inverses and something and so on and so forth. Okay? As to, I don't know the answer to your question. I don't know the answer to your question. Okay? Because I learned this proof from somebody else. And the professor that I learned it from probably learned it from somebody else. I don't know whether he came up with that or not. I'll tell you explicitly where I learned that from. Back when I was a postdoc, I guess, doing postdoctoral work already, because I didn't know any group theory when I was still a graduate student. So afterwards, when I was a postdoc and had to do some research, and I realized that group theory is very important. I was doing atomic molecular physics at the time, okay? And you know that in order to find the spectra of molecules and atoms and so on, symmetry properties become very important. And the symmetry properties, in fact, dictate to a large extent the possible energy eigenvalues that a system can have. And so I had to learn some group theory sort of pretty fast on my own. And it so happened at the time I was at the University of Rochester. I was in the chemistry department, actually. But in the physics department, there's this famous professor by the name of Okubo. I guess it's Japanese-American. Professor Susumu Okubo. I don't know if you've heard of the famous formula in high-energy physics called the Okubo-Gelman mass formula. You will come upon it if you study high-energy physics. He gave an excellent course in group theory, which I took, and in there was this proof, which I copied down. Okay, and I put it into this book. Interesting story about Professor Okubo. He was Japanese-American, so his physics and math was excellent. But he spoke English with a heavy Japanese accent. And and he would be doing something like I'm doing here, except that he would be doing it much faster. So when I sat down in a lecture class following his class, you would hear throughout the course of an hour from the beginning to end, I, J, K, L, L, alpha, mu, nu, F, rho, J, K, pum, pum, mu, nu, pum, pum. It's like a sing song. Mu, nu, mu, 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 mu. I'll go on for the entire, for the entire hour. Okay? But, things were so detailed and so clear that, as this proof indicates, that it was very valuable, at least for me. Okay? Another interesting thing was, I don't mean to offend anybody in here, but I guess Japanese, if you're a native speaker of Japanese, you don't pronounce the letter L very clearly a lot of times, so the L becomes an R, okay? Or the R's becomes L's? Really?
My aunt used to live in Japan.
Oh, I see.
Her name is Robin.
So it becomes Robin? Okay. In any case, the electron becomes an erection. And very often the relativistic electron would become a relativistic erection. So we all right. Okay. Oh, but Professor Okubo, I learned so much from him. Unfortunately, he recently passed away. All right, let's go back to basic group theory. We do have to understand a little bit more about groups in order for us to proceed. Now, we have already given the definition of a group. So a group is, you have a set of objects. That's called a set G, and the elements are called G1, G2, and so on and so forth. So a group is basically a set of objects with a multiplication rule imposed, so that anytime you have two elements, G1 and G2, both in G, you can make use of this multiplication rule written in the order specified, because multiplication is not necessarily commutative in a group. The first rule is a closure of multiplication, which means that if G1 and G2 are both in big G, then G1 times G2 is also something in big G. That's called a closure property of group multiplication. Okay? The second property is this associative rule of multiplication. Given three elements, G1, G2, G3, all of which are in the group G. So you can multiply G2, G3 first to obtain another group element in G, and then you can multiply to its left by G1, and the whole thing will still be a group element in big G. This is supposed to be the same as doing the multiplication in this order. Okay? You can multiply by, so that when you write down the product, you don't need to put the bracket at all. Okay? The meaning is automatically unambiguous because of this so-called associative rule of multiplication. The third one is that inside the group there must exist a very special privileged element called the identity element, so that when you take this identity element and multiply by anything either to its right or to its left, then you get back this G, whatever it is. Okay, so the E is called the identity element. And from this, number 4, given any G, there exists an element which is called the inverse of G, which is unique to G, such that G inverse of G is equal to the identity element. Given this fact alone and the third property, you can also prove that G inverse G is equal to GG inverse. So a group element multiplied by its inverse can be carried out in either order, and both of which has to produce the identity element. Any set of elements with a given multiplication property which satisfies these 4 conditions is called a group. Okay? Yeah?
There's no need for a zero element in this case?
There's no need for what?
A zero element?
The zero element is the identity element of the additive group of numbers. Right? So that 0 added to anything else is that something else. Okay? And the inverse of that element is called minus G. Okay? So the G added to minus G gives you 0, which is the identity element. Okay. So this is very general group, and as I mentioned, the perfectly trivial group is the group consisting of only the identity element. Okay. So that all these properties are easily seen to be satisfied. So, but it's a good group. Okay. Another group consists of two elements, also very important. Now this one is not important because it's so trivial. The other one consists of two elements, G, one G and another one called E. Okay. With the perfectly simple multiplication table, this is called a dihedral group, by the way. There are two elements in here. Okay. Multiplication table is very simple. This is G, E, G, E. Okay. So there are four multiplications, right? G times G, and E times G, and then G times E, and E times E. And the definition is very simple. G multiplied by itself is equal to E. So G is the inverse of itself in this simple group. By definition, G multiplied by E is G, G multiplied by G is G, E multiplied by. So that specifies this group. It's called a dihedral group, which is very important also, as you'll see. And there are trihedral groups, so that G cubed is equal to E, and so on and so on and so forth. Plus, there are finite groups, or groups, like these are both finite groups, group of one element, group of two elements. Finite group is a group of finitely many elements. The elements can be countable, 1, 2, 3, and so on and so forth. A symmetric group is a finite group, right? As I mentioned, so if you have the group S3, which is called the symmetric group of order 3, which is a group consisting of permutations of three things, and there are 6 elements in there, because there are 6 possible permutations of 3 things, okay? And you can kind of combine those permutations to give you yet another permutation. So you can define the multiplication rules very well, and you can these group elements are not commutative, okay? And you can write down examples to show. And then you can show that the simple rule of composition used as multiplication will satisfy these properties, so that S3 is a group of 6 elements, so it's a finite group, okay? And all the Sn are finite groups. Sn has n factorial elements, right? So now, this is also a very important group, as I mentioned already. That the symmetric group is very important because in quantum mechanics, the particles are considered as indistinguishable particles. So you have to understand what happens to the wave function of a physical system if you interchange the coordinates. That is, when you permute the coordinates. Okay, in that case, the wave functions have to satisfy certain symmetry requirements. They're either symmetric, totally symmetric, or totally anti-symmetric, depending on quantum mechanically whether the system consists of a system of bosons, a system of fermions, and so on and so forth. So these are very important. Plus, the representation theory of the symmetric groups is closely tied to the representation theory of the important Lie groups that we are studying, such as SON or SUN. Okay, so these two kinds of groups, the Lie groups on the one hand, which are infinite groups because they consist of infinitely many elements, and the SN groups should be closely studied together because the representation theories are very closely connected. Now in this course, unfortunately, the whole course, we do not intend to devote the whole course to group theory itself. So we'll just kind of focus more on the Lie groups as we have been doing. If you really want to go into this symmetric groups, this will take at least another half quarter. So unfortunately, we're going to have to leave the symmetric groups alone. Okay?
So SN is not a Lie group.
It's not a Lie group. It's a finite. Lie groups are all infinite groups, or continuous groups. The parameters defining the group element have to occupy a continuous range of values. That's why the Lie group is also a differentiable manifold in its own right. It is a couple of things. A Lie group is a differentiable manifold. At the same time, it is a group. Okay? Yeah.
I was asking something similar.
Yeah.
But a Lie group, does it have to be infinite?
Yeah.
Or can it be finite and continuous?
And a Lie group is infinite because by definition, a Lie group is defined a particular group element in a Lie group is defined by a particular set of parameters, and all those parameters occupy a continuous range of values. Because of this, then there are necessarily an infinite number of elements in the Lie group, which are not infinite, also not countable. Okay? Take SON, for example, right? SO3, for example. SO3. SO2, for example. Okay? SO2, there's a rotation in the plane, just, depends on an angle. Okay? And this angle can vary anywhere between 0 and 2 pi. All right? Infinite number of values for theta. So how many rotations are there? An infinite number of rotations. One is characterized by a particular value of theta between 0 and 2 pi. Okay? So now, it's at the same time a differentiable manifold because it's isomorphic to a circle, right? A circle is a group. It's called S1, as a matter of fact. It's a manifold. It's S1. And a particular point in here is characterized by some coordinate that we call theta. Okay? So this group is SO2 is topologically equivalent to a circle, but at the same time, it is a commutative group. It's a abelian group because if you have two rotations, theta 1 and theta 2, it doesn't matter which one you go first. SO3 elements are not commutative. SO2 elements are commutative. Yeah, there was a question?
So for the SO2 group, there's two basis vectors in SO2.
The group is not a linear vector space, so therefore you cannot talk about basis vectors in a group. The algebra is a linear vector space. It's a one-dimensional vector space because there's only one parameter. Okay. All right? There's only one parameter. All right? In other words, you take a point in here, the linear vector space is, you can think of it as a tangent line at that point, the point at the identity. Okay? So, like that. Okay, so one-dimensional linear vector space has one basis vector, whatever you call it. Okay? Any more questions before we go on? Okay, so now the general concept of a group is very simple. I mean, that's it. That defines a group for you. And it's quite amazing that group theory, just based on this definition, develops and can flower in all sorts of ways. Okay, in particular, it finds applications, very important applications in fundamental physics. Okay? All right, so now we have about 10 minutes. Let me just bring up the first important concept aside from the definition in here. The first one is a subgroup. Okay? And it's a very simple definition. Let's say you have a group. Okay? You have a group. And supposing I find a subset in here, which consists of the same identity element, and everything in this subset is in its own right a group in itself. In other words, using the same original definition of multiplication, this subset is such that you take any two elements and multiply them together by the original multiplication rule, is still something inside the same subset. So a subgroup is a subset of the original group, which is in its own right a group. That's why it's called a subgroup. Okay? Being a group in itself, it has to have the identity element. Being because it uses the same multiplication rule, the identity element of the subgroup is the same identity element as in the larger group. The idea of a subgroup will be very, very important because later on we're going to have to use it. We can use it to formulate the definition of a so-called quotient group. A quotient group is where, let's say you have a group in here, okay? And let's say this is, original group is G, this is a subgroup. Now the subgroup has to satisfy a certain property. I'm not going to mention it explicitly now, which is called invariance property, in the sense that GH is equal to HG, okay? So that H is equal to G minus 1 HG. You can write it like that through us, where G is any element inside the bigger group itself, okay? If the subgroup is such that this is true, what this means is that if you take any element in H, multiply it by G on the left-hand side, is the same as multiplying it by G on the right-hand side for any element in H, okay? Then this is called an invariant subgroup, H. And if you have an invariant, now not all subgroups are invariant subgroups. In other words, not all subgroups satisfy this property. Whenever you have an invariant subgroup which satisfies this property, then we can bust this group up into disjoint sets, like so, disjoint. This is like the ordinary process of division, okay? Such that there's a well-defined multiplication between each of these things in here, okay? The multiplication is such that the original group H itself is the identity, okay? You take as elements these different, sometimes called cosets, okay? And so there's a new group that can be formed whose elements are these cells, so to speak, with this one being the identity element. I'll go through in detail how you do that later. This is a very important concept in group theory. And you then produce a quotient group, which is usually written as G divided by H. It's kind of like the ordinary idea of division, where you have your 6 divided by 3 gives you 6 divided by 3 is 2. So, so it gives you 2 groups of 3, something like that. Okay? Something like that. That's why this is called a quotient group. I'll go through this in detail later. So the first concept that we need in order to lead up to all that is the concept of conjugacy class in a group. So you have a group G, okay? A conjugacy class is defined by what is called an equivalence relation between elements in the group. And let's say you have 2 elements in a group. 2 elements in a group are said to belong to the same conjugacy class if there exists some P in G such that the 2 are related to each other by the similarity transformation produced by P. Like that, okay? You take any 2 elements in a group. If there's a P somewhere else in the group such that G1 and G2 are related in this way, then the 2 elements are said to belong to the same conjugacy class. Now you can show that this conjugacy class is a relationship, okay, in this sense. This fundamental mathematical idea of what is called an equivalence relation among different things in a set, right? An equivalence relation is something like this. Something is always related. If 2 things are related to each other, we use this symbol, okay? X related to Y. Some relationship that you can think. This is one such relationship, okay? G and 2, if G and 2 are related by this relationship, then G1 and G2 are said to be equivalent. In this case, in the sense that they belong to the same conjugacy class. So you can show that the concept of conjugacy in group theory is a very special case of an equivalence relation in basic set theory. An equivalent relation has to satisfy 3 properties. Number 1 is that something is always equivalent to itself. And the second thing is if 2 things are related to each other, then they are related in the opposite order also. Okay? Number 3 is that if X is related to Y, and y is related to z, then it follows that x is related to z. This kind of transitive relation. Any relationship which satisfies these three properties is called an equivalence relation in the set. Yeah, two questions. Let me answer yours first.
Can you expand? I'm sorry.
Huh?
Who are you talking to first? Okay.
Go ahead.
Can you expand on the first point, because why would it not be that?
Why would it not be that?
Or why would it not be related to itself?
Well, this is something that's just stuck in there for completeness. Okay, so you can say a relationship of a father and son. Okay, so two people are related to each other if one is the father of another. Okay, so unless you have a son who is also the father of himself, then this is not relationship. You see what I'm talking about? Okay, all right. So this is put in there for the relationship to formally satisfy the concept of what is called an equivalence relation. Let me go to your question.
So does that imply the equivalency classes are the cosets?
No. Yes. Later on, we'll come to the cosets. Yes, I think that is true. Okay, I think that is true. But let me defer that discussion for the time being. Okay, the cosets that I refer to here needs to be further defined. I haven't defined for you there are two different kinds of cosets: left cosets and right cosets, and so on. Group theory. Okay, because multiplication is not commutative. I'm just sticking with this general concept of the conjugacy class. Okay. So you can prove very easily that this conjugacy concept is a very special equivalence relation, okay, which is defined for any set in general. Now you can also show quite easily, and I'm going to leave you to do it, that any equivalence relation necessarily busts up a set into disjoint sets, okay. In other words, if you have a set, whatever it is, may not even be a group, okay? You introduce an equivalence relation which satisfies those three conditions, you can always use that equivalence relation to kind of split up the set into disjoint sets, okay? What it means is that if two things, you cannot have such a thing where two of those intersect in there's non-zero, there's a non-null intersection of these two circles mean that everything in the first circle is related to each other, and everything in the second circle is related to each other, okay? So you can prove that if there is something which is related to both circles, that something can only be the null element in the set. Yeah?
So elements in the quotient group are the equivalence classes?
Yeah, they are elements in the quotient group are the equivalence classes. Yes, that is true, I think. Okay. Now, but let's not talk about quotient groups first, because I haven't really defined that for you. Okay. Let's just talk about this conjugacy class first, which has been defined for you. And so you can prove quite generally that, quite easily, in fact, that the relationship defined by the concept of conjugacy class is in fact an equivalence relationship, so that necessarily the conjugacy classes are disjoint. Okay, that means if I go back to talk about a group in here, that if something is within one conjugacy class, it cannot be within another conjugacy class. All the conjugacy classes are necessarily disjoint from each other, meaning that the intersection of two conjugacy classes must be what? The null, what is called a null set. Okay? All right? In fact, this is problem 1. I'm asking you to prove that that conjugacy classes are necessarily disjoint, where conjugacy classes are defined in this fashion. Okay? So let's stop here today. I think we ran out of time. So next time we come back, we continue with this, developing this concept. We will then go into the cosets, left cosets, right cosets, and then in invariant groups, and then the quotient group, and so on and so forth.